Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome to lecture 31, Organic Chemistry 1. Today we will continue on chapter 8, Structure, Synthesis and Reactions of Alkenes. Alkene synthesis, dehydrohalogenation of alkyl halides. We have covered this topic before in lecture 26 and 27 of Organic Chemistry 1 series. The E2 dehydrohalogenation gives excellent yields with bulky secondary and tertiary alkyl halides. A strong base forces second order elimination E2 by abstracting a proton. The molecule's bulkiness hinders second order substitution and a relatively pure elimination product results. So the base attacks on the hydrogen, abstracting the hydrogen, forming here carbon-carbon double bond and X out simultaneously, so it is transition state, one-step reaction. The hydrogen and halide should be anti-coplanar with angle, theta angle is 180 degree. Could be in some rare examples where the H and X are in what we call it eclipsed form and theta angle is 0. And that's very rare, okay? Bulky bases can minimize the amount of competing substitution. Large alkyl groups on a bulky base hindered its approach to attack carbon atom for substitution, yet it can easily abstract the proton for elimination. Some of the bulky strong bases commonly used for elimination are tertiary butoxide, diisopropylamine, triethylamine, and 2,6-dimethylpyridine. Tertiary butoxide, diisopropylamine, triethylamine, and 2,6-dimethylpyridine. As an example, if we have here bromocyclohexane with dipropylamine and heat, you get the hexene in over 90% yield, so it's almost. Bulky bases can also accomplish dehydrohalogenation that do not follow Zaitsev rule. Remember Zaitsev rule that we are expecting always from the dehydration reaction to give the more substituted alkene because they are more stable. So because of the steric hindrance often prevents a bulky base from abstracting the products that leads to the most highly substituted alkene. In these cases, it abstracts a less hindered proton, often the one that leads to the formation of the least highly substituted products. This is called Hofmann Product. So if we start with 1, 2, 3, 4, that's 2-bromo, 2-methyl-butane with small base, strong base like ethoxide. The base will attack on the hydrogen, abstracting the hydrogen, forming double bond, Br out. That leads to the formation of Zaitsev, the most substituted alkene. Here is tri-substituted. It's 2-methylbutene as a major product, and following Zaitsev rule. Also, it gives minor products if it attacks on the terminal, this hydrogen, forming a double bond, getting Br out. That is Hofmann product. In this case, we will able to detect or isolate minor product of 2-methylbutene. Let us now try the tertiary butoxide, the bulky base. The bulky base, to abstract this hydrogen, will be a little bit difficult because of the steric effect, and you will see that the 2-methylbutene minor product, while the 2-methylbutene will be a major product. Why? Because in this case, the base will go and abstract this hydrogen much more easier. The rate of this elimination will be faster, product will be higher. Make models of the following compounds and predict the products formed when they react with the strong bases. The best way to really visualize the organic reaction mechanism is to build models. So you have to have models. If you don't have a real model, you can use a computer software, as I do, to visualize the stereochemistry of the molecule. So here is a compound drawn for you in Fischer Projection, and telling you that you react this compound with potassium hydroxide, and predict the products. So the first step, I took this molecule, draw it in 3D. Okay, I took this molecule, I know from Fischer, okay, this is Fischer, right? This is Fischer projection. This means that this PR is up, 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 up. And this and that are down, down. This is how actually we draw Fischer projection. I took this structure, put it in 3D mode, and obtained this configuration. So the BR is up, CF3 right, H left, and then on this carbon, the carbon in front, hydrogen right, ethyl group is left, CH3 in the bottom, here is CH3 in the bottom, left, everything's fine. Okay. For the dehydrohalogenation, the Br and the H should be anticoplanar. So I have to rotate the molecule, the carbon-carbon bond, hydrogen will be down, CH3 will be up, and CH2 H5, C2, H5 will be on the right. Okay, here we have it. Now the hydrogen and Br are anticoplanar. Base will attack on the hydrogen. The 2 electrons moves to form a double bond. Br will be out. Accordingly, we will have double bond in here, and CF3 and CH3 are opposing one another. CF3 and C2H5 will be on the same phase. That if we actually have E2 mechanism, so that's E2 product. On the other hand, since this one is secondary alkyl halide, we are expecting also that we have competing reaction SN2 from the back side of the BR, right? So the OH will be down and CF3 will be right and H will be left, and that is SN2 product. Pretty easy, right? Okay. If we have meso 1,2-dibromo 1,2-diphenyl-ethane, okay, take the compound to 3D or build up a model. This is PR, this is phenyl right, this is hydrogen left. Hydrogen, phenyl, Br. In front, you have H right, phenyl left, Br down. Br, phenyl, hydrogen. We need the hydrogen to be anti-coplanar to Br, so we have to rotate the carbon-carbon bond. The phenyl will be on the right, Br will be on the left, and hydrogen will be down, anti-coplanar. Then the base, now its base is bulky, triethylamine, bulky one. So we are expecting elimination product. Good. Okay, so the abstracting hydrogen, these 2 electrons will form a double bond, and Br is out. So we get the cis configuration product, the cis product. Okay, the 2 phenyl group are on the same direction. We can also say that is E. Why? Because on this carbon, phenyl is superior. This is number 1 group. On this one, Br or phenyl? No, Br. So this is G1 on that carbon. So according to the name, rules, this is E. Or because these 2, the same group, phenyl, are on the same direction, we can call this cis. Given 7-bromo bicyclo 2,2,1-heptane with sodium hydroxide, strong base, we will find that SN2 is the only mechanism possible because there is no H coplanar with Cl. An elimination product would violate Bredet's rule. Building 3 model for this molecule, we will find that the carbon Cl bond is not coplanar with the carbon hydrogen bond on the adjacent carbon. So theta here is not 180 as usual or 0. So the only expected product will be the substitution and the formation of bicyclo 2,2,1 heptane 7-ol. Starting with 1s, 2s, 3d, 4r, 2-chlorobicyclo 2,2,1 heptane 3 deuterium with bulk base like tertiary butoxide. The product is 1r 4s bicyclo 2,2,1 hept 2-ene with the elimination of Cl deuterium. We have studied this problem before, but I'm just getting it here so to practice one more time. Making 3D of it, you will find that the carbon Cl and the carbon deuterium are coplanar. The carbon Cl and carbon CH are not coplanar, so the elimination will take place by elimination of deuterium chloride and the formation of bicyclo 2,2,1 heptane 2-ene. The hydrogen cannot be anticoplanar with Cl, and the elimination must take place with syn-coplanar orientation. Then deuterium will be removed. Reacting of 1s, 2s, 6r, 1-bromo 2-methyl cyclohexane 6-deuterated with methoxide as a base. What do we expect as a product? Here the BCl is down, Br is up, and deuterium is down. Building a 3D structure, okay, here is the methyl down, Br is up, and deuterium is down. This is a structure, okay. Now, for the E to occur, E2 mechanism, Br and the leaving group hydrogen should be coplanar, anti-coplanar. So if we make a flip, this is the predominant major conformation. Okay, now if we make flip, CH3 will be axial, Br will be axial, and the deuterium will be coplanar, anti-coplanar position. So the methoxide will abstract the deuterium, 2 electrons will move to form a double bond and Br is out. Okay, the Br and the adjacent hydrogen are not anticoplanar, so we cannot eliminate this hydrogen and that one. The only one available according to E mechanism is the deuterium. So the product will be S3-methyl cyclohexene, and the configuration around this carbon will not change. This is the same S configuration. And these two compounds will not form. okay, because these hydrogens are not anticoplanar with the Br in this form or in that form. Starting with 1R, 2R, 3S, 2-bromo, 1,3-dimethyl cyclohexane, reacting this molecule with sodium methoxide in methanol, the only product is SN2 product, and the formation of 1R, 2S, 3S, 2-methoxy 1,3-dimethyl cyclohexane. As you know, the reaction took place on the Br, carbon number 2, so you will find that the change in configuration occurred on 2, from 2R to 2S. And no elimination product, since there is no coplanar hydrogen to Br. If we take this molecule to the 3D structure, this is the Br, anticoplanar with the methyl. Here is the hydrogen is not coplanar. The other hydrogen here is not coplanar. So there is no elimination of HBr. The E1 dehydrohalogenation, first order dehydrohalogenation, usually takes place in a good ionizing solvent, such as alcohol or water, without a strong nucleophile or base to force second order kinetics. The substrate is usually a secondary or tertiary alkyl halide. First order elimination required ionization to form a carbocation which loses a proton to a weak base, usually the solvent. In E1 dehydrohalogenation is generally accompanied by SN1 substitution because the nucleophilic solvent can also attack the carbocation directly to form the substitution product. To practice on that, propose mechanism for the following reaction. 1-bromo, 2-methyl cyclohexane, heating this in ethanol will lead to formation of 5 products A, B, and C, and D, and E. Propose mechanisms for their formation. Since we have very weak nucleophile and dielectric solvent, good dielectric solvent, so we are expecting that the secondary alkyl halide will ionize to a secondary carbocation. That's the first step. Second step, attack of the nucleophile on the carbocation, forming oxonium ion, and then proton transfer to alcohol solvent molecule, formation of A1. So we call that SN1 product without rearrangement. Now we have here secondary carbocation, hydride shift led to the formation of tertiary carbocation. Then, after the formation of carbocation tertiary, nucleophilic attack, form oxonium ion, again proton transfer to form compound B, that's SN1 product with rearrangement. For the secondary carbocation, we have here CH and another CH. So the solvent could eliminate this one or that one. Elimination of the green one okay, will lead to the formation of compound D. Formation of the blue hydrogen led to the formation of compound C. So these two are E1 products without rearrangement. After the hydride shift, the tertiary carbocation has 3 hydrogens around on the adjacent carbon. These two are the same, equal. So if we eliminate the green one, that will lead to the formation of D. Elimination of the blue one will lead to the formation of E. So D and E, we can get D from E1 without rearrangement. Also we can get it from the rearranged carbocation plus E. So D and E, we can say it is E1 products with rearrangement. Depromination of vicinal dipromide, we can eliminate Br as sodium bromide and iodobromide by reacting the vicinal dibromide with sodium iodide in acetone. The iodide will attack the Br, abstract Br, leaving 2 electrons to form bi bond, and then Br minus will be out as sodium bromide. This is in E2 mechanism, so these two Br should be anticoplanar. Br are in anticoplanar position for this reaction to occur. The following compounds show different rate of depromination. One reacts quite fast and the other seems not to react at all. Explain this surprising difference in rate. Okay, Br is up, down, and here is up. This is fast, and you can get 4 tertiary butyl cyclohexene, while if this is up, this is down. But the tertiary butyl group is down. React this with potassium iodide, no elimination and no reaction almost. Explain that. Compound 1R2R4S 1,2-dibromo 4 tertiary butyl cyclohexane, whereas the Br here is up and Br here is down, and the tertiary butyl is up. Drawing 3D, Br is up, Br is down, and the tertiary butyl is up. Br is up, down, and this group is up. We will find that this major contribution in the configuration, this conformation is the most stable conformation of the 2 possible chair. The other one will be here equatorial, but the tertiary butyl group is axial. That's not stable, so this one is more stable, and the reaction will take place because the Br are anticoplanar. Okay, 1R, 2R, 4R, 1,2-dibromo 4 tertiary butyl cyclohexane. Br is up, Br is down, but the tertiary butyl is down, which means that it is in axial. Okay, and this conformation is highly unstable because again the tertiary butyl is axial, and the major one will be equatorial, and equatorial. This is highly stable and the most stable conformation, so the compounds will exist very nearby, up 95% on that conformation, so no elimination E2 will take place. Predict the elimination products formed by Debromination of the following compounds with iodide ion in acetone. Include stereochemistry and give a correct name for each product. For the 1R2S12-dibromocyclodecane, its 10-member ring, this is down, down, so this is down, down. For the reaction to take place, you have to have these two Br anticoplanar. The molecule is flexible enough, okay, and we can rotate around this carbon bond to get the Br up and keep this one down. So, and in that position, the E2 and the elimination of Br, IBr, and sodium bromide can take place. Iodide attack on this one. See the position here of the alkyl group. The alkyl group around the double bond, one is up here and the other R will be on the opposite direction, so we are getting trans, or what we call it E-cyclodecene. E-cyclodecene. Starting with 1s, 2s, 3s, 1, 2, 3 tribromo, 1-ethyl, 3-methyl cyclohexane. Br is down, CH3 is up, Br is down, CH3 is hydrogen is up. Here is Br is up and the ethyl group is down. Okay, so again here is up, Br down, up, hydrogen, Br is down, Br is up and the ethyl is down. In this conformation, these two Br are anticoplanar, okay, and this conformation is the more stable than that one, where the Br axial, equatorial, equatorial, and the ethyl group is axial, so the shift will be going to this more stable conformation, where these two Br are anticoplanar and the elimination will take place for this one, and these two Br are not axial anticoplanar in this conformation or in that conformation, so we cannot eliminate this Br and this Br. Here is this Br with this Br cannot be eliminated, and the only product is S3 promo 1-ethyl 3-methyl cyclohexane. See you in the coming lecture. Bye bye.